All right, today we're going to be talking about graphs. And I just wanted to give you all a very quick introduction to graph theory because I think it just helps us visualize things better. So graphs, and we've talked about graphs several times. You've probably hit them many times in your mathematics career. So a graph is basically, we have an XY coordinate plane. And you'll notice that I'm actually very bad at drawing. But the nice thing about being bad at drawing is it forces you to use your imagination to understand how everything should work. So let's imagine the function y equals x squared. This is the parabola formed by y equals x squared. Now let's say that I wanted to move that graph up one space. How would I do that? Well, if you think about it, what I really want to do is I want to take every point on here and move it up one. Well, where does the point come from? The point comes from this function, okay, x squared. So if that is the output of the function and I want to move the output up one, what should I do? Well, I should bump it up by 1. So if I wanted to take this graph and turn it into this graph, then I would write the equation as y equals x squared plus 1. So I've simply taken my previous function and added 1 to move it up. Okay. Now it's a little bit more complicated if I want to move it left and right. How would I move it left and right? Well, the way that you move a graph left and right, so let's say I wanted to move it to the left. I want to move it to the left by 3. Okay, so that I'm moving it 3 in the negative direction. But my original graph is y equals x squared. To move it to the left 3, I replace x with x plus 3. So this would be 1, 2, 3. I'll have my graph here. Okay, and so you replace the variable with the negative of what you're wanting to do. Because here, since we're going to the left 3, it's a negative 3. So I replace every instance of x with x minus 3, which is x plus 3. Now you might say, well, why did we add to get y, but we subtracted? In this case, subtracting a negative gave us adding the x. Well, the fact is that we actually did the same thing both times. Because in the case of the y, when we added it to the right side, that was the same as subtracting it from the left side. So let's look back. So we had y equals x squared, and we changed that to y equals x squared plus 1. But let's look at that from the point of view of what happens if we modify y rather than modifying x squared plus 1. If I subtract 1 from both sides, get y minus 1 equals x squared. So I have replaced my y with a y minus 1, and that moved the graph up. And likewise, if I replace my x with x minus 3, it'll move the graph to the left. Okay, so I can say y minus 1 equals x minus 3 squared. And this is the same as x plus 3. So in order to shift a graph in any given direction, you replace the variable that you're wanting to shift with the variable minus the amount that you want to shift it. Okay? So this is true even in complicated equations. So let's say we have y squared plus x squared minus 5x plus 4y plus 3 equals 0. All right, so that's quite a mouthful. And let's say that we wanted to shift this graph up by 2 units. Okay, what we would do is, since we're going up and down, that's on the y-axis. So we would have to replace our y. We're going to go up 2 units. So we're going to replace our y's with y minus 2. Here's another y. Now, let's say that we wanted to shift this same graph. We want to shift it to the right by 3. Okay? Shifting to the right, that's shifting on the x-axis, and shifting to the right is in the positive direction. So I'm going to replace all of my x's with x minus 3. Y minus 2 squared plus x minus 3 squared minus 5 x minus 3 plus 4 y minus 2 plus 3 equals 0. So this new equation is the same as my original equation, just shifted up and to the right. And this actually becomes even more complicated if I actually take the square of these and expand them out. But you can see that the process of taking a graph that we know and generating a graph that's shifted is actually very straightforward. Now, what's also interesting is that most things in mathematics you can interpret both as formulas or as graphs. And different people think different ways. Some people think more clearly in terms of graphs, and other people think more clearly in terms of formulas. I'm more of a formula person, but some people are more graphical. So if we think about a function, and let's just do, for simplicity, let's just do y equals 2x. Okay, so we'll have this function. So y equals 2x, it's going to be a line, goes infinitely both directions. All right, so this is y equals 2x. If I want the inverse function, all I have to do to get a graph of a function and turn it into the graph of an inverse function is to reflect it over the line y equals x. So that's going to be a straight diagonal. And the inverse function will simply be a reflection of this line over this axis. Okay, so what is the inverse function of y equals 2x? Well, the inverse function is y equals 1/2 x. Because if I multiply something by 2 to get back the original number, I just half it. Okay, so that's going to be, but you can see that if I reflect this over that line, over this axis, then it becomes the inverse function. And that's true of anything. No matter how complicated your graph is, to go from the function to the inverse function, all you have to do is reflect it over this line. So that helps you sometimes if you ever have a function that all you have is the graph, and you don't actually have a formula for it. you can develop the inverse function just by taking that graph and reflecting it. So now I wanted to give you a little bit of description and intuition about specific kinds of graphs. Okay? So the most popular that you've probably run into so far are polynomials. Now, polynomial simply means that we're going to set y to a function of x, where x is going to be raised to some sequences of powers. Okay, so this is a polynomial. And so polynomials have a very interesting property, and that is the given the biggest, if you look at the biggest exponent of a polynomial, the number of humps that your graph has will be at most the biggest exponent minus 1. So this graph, the graph of this function, will have at most 2 humps, because 3 minus 1 is 2. And so it will look something like this. Okay, so we have 1 hump and we have a second hump. So think about what you know about quadratics, right? Quadratics, if I have y equals x squared, that's going to give me a parabola. Now, this is also a polynomial. Quadratics are polynomials. And so x squared, my biggest exponent, is 2. Well, how many humps will my graph have? At most, if I subtract 1 from the 2, I'll get 1. And this has at most 1 hump, which we can see right there. And so it doesn't matter how complicated your equation is. X to the 7th minus 25x to the 3rd plus 77x squared minus 3x plus 1. Because 7 is our biggest exponent, the graph of this function will have at most 6 humps. Now it might have fewer humps, but it won't have more than 6 humps. So it will, it could graph something like 1, 2, 3, 4, 5, 6. So this is the highest exponent is known as the degree. And so the number of humps equals the degree minus 1. So 1, 2, 3, 4, 5, 6. And that is the most number of humps that a 7th degree polynomial can have. Okay? Now, if you've done trigonometry, you've dealt with the sine function. Okay, so the sine function looks something like this. And it oscillates, it starts at the origin, and it goes up to 1 and down to -1. And it just does that over and over and over again forever. And it's known as an oscillating function because it's going back and forth and back and forth and back and forth and back and forth. So this is sine, and cosine is almost identical, except it's just shifted over. That is probably not the best drawing of cosine, but the main thing to keep in mind is that when sine is 0, cosine is 1. So it starts up here rather than at the origin. Okay, so it is the exact same graph as sine, just shifted. Now the interesting thing about sine and cosine so you can see that on sine, for every x value, there's only one y value. But the inverse function is not equivalent, because if you remember, we get inverse functions by reflecting over that line. And if you reflect this over that line, you get a function that goes up and down forever instead of going sideways forever. So any given x value will actually generate an infinite number of y values. Usually what they do to simplify this is they just say, well, we're only going to allow it between here and here, and that will give us a true function where one variable yields one result. But nonetheless, they're valid values all the way up and down, because if I reflect this, it'll be going up and down. Another good function to be aware of is the exponential function. And the exponential function looks about like that. So it goes forever, and the exponential function is y equals some number raised to the x power. Okay, and so notice that anything raised to the 0 power is 1. So at x equals 0, this has to be 1. The n can stand for any given number. It's not a variable, it's just there are several exponential functions, and they each, so I can say y equals 2 to the x, y equals 7 to the x, or there's a special number, y equals e to the x, and e is a special constant, which we will talk about in later videos. But all of them share a very similar looking graph, especially if we don't mark the numbers. They all intersect at, they will have a y of 1 when x equals 0, because all of these raised to the 0 power are still 1. And they'll all have the same basic look. Now the inverse function to an exponent is the log function. And so the log, again, is what happens if I just reflect this over the y equals x axis. And so it is simply the reflection over the y equals x axis. Math is misleading. What do I mean by that? Why do I say that math is misleading? Well, in mathematics, we tend to study things that are studyable, okay? And the things that we find most studyable, especially in calculus class, are graphs that are smooth and continuous, okay? So, but the fact is, I mean, you've seen, most of the graphs that you've seen in your entire life are either lines or curves or something where they're smooth and continuous. And so it's very tempting to think about, after you do math for a long time, to think about all of life being consisting of smooth and continuous functions. But that isn't reality. That is simply what we can analyze of reality. And so it's always good to think about what are other possibilities that could be that we just can't see because we can't analyze. So for example, a hard function to analyze So this is a function. It's an ugly function, right? We don't imagine that there's a lot of processes like that, but part of that is a failure of imagination, okay? There are things in life that are messy, and simply presuming that life itself must follow the rules of math is a temptation that a lot of people fall for. Life itself is messy. It doesn't always follow what we expect of it, what we want of it with these smooth continuous functions. So my only point in this is just that it's very easy to fall in the trap that the things that we're able to study and able to study well are equivalent with reality. Okay, so reality is whatever reality is going to be. We don't have any control over reality. What we do have control over are the things that we think about. And we tend to think about the things that we can understand. And we try to broaden our understanding over and over again. But at the end of the day, our understanding is limited compared to the size and scope of reality. And so it's dangerous to assume that the limits of our thinking are equivalent to the limits of reality. And I just wanted to throw that in because sometimes we spend so much time doing these problems that have simple solutions, that have analyzable problems, that we just tend to fall into this trap of thinking that everything must be like that. And I just want to let you know that all of life isn't like that, and that we shouldn't assume that it is. So that's graphs of functions for you, and I hope you join us for our next video. We'll start diving into actual calculus in the next video.